All right, hello everyone. Let me get the camera to follow me, maybe. And I hit start stream, Okay, hello everyone. Welcome to today's CSE365. Getting closer and closer to the end of the semester. I think there's like, what, less than a month or something. Jan is not here today. He's not feeling super well. So what we're gonna do today is we're gonna dive into a sort of demo problem that is heavily inspired by the ideas in this module that should hopefully further clear up any confusion about how to approach this sort of task of reverse engineering. Okay, before we do that, we're just going to do a quick course, like what's going on in the course. So this is how Computing 101 went. Pretty good, certainly compared to cryptography, for example. Looks like the median student got an 80%, which is pretty good, and most of the class passed. Okay, this is how reverse engineering is currently going. A lot of people finished up the checkpoint, makes sense. The few challenges after the checkpoint are difficult, okay? So highly, I know we say this every single week, but I highly encourage you to start now. And there's also the bonus issue that we talked about last week, which is that on the day of the deadline, home college will not go down, right? We're finally stable. It's good to go. This time for real. But IDA, if you're liking IDA and you're liking IDA's decompilation, almost certainly that will fail on the last day because everyone is going to swarm into the server, work on the assignment. And here's the issue with IDA. We didn't build IDA. We have no control over IDA. I don't know if we're crashing IDA decompilation servers or they're rate limiting us. Whatever it is, that decompilation thing goes to the cloud and it's going to fail. So if you like IDA decompilation, start early. Alternatively, feel free to use Ghidra decompilation or anger management decompilation or binary ninja decompilation. There's other decompilation tools out there that work very well, especially on these challenges. But if you feel like you like IDA, maybe you started this assignment using IDA, keep that in mind. IDA will fail on the last day. Okay, so that's what we'll say about that. Additionally, I know a lot of students are struggling with kind of some of these middle challenges. And I've seen some people talking about, right, it's a new module, so I can't say like, oh, this is how people did it last semester. We deployed this new reverse engineering module. What I've seen as some sort of consensus is, these next few levels after the checkpoint are difficult, but then maybe you kind of like build up an understanding and then like the later levels actually end up getting easier. There's kind of like a hump of reverse engineering that you need to get over where you understand kind of the core of the program a bit better. And then once you've kind of developed that understanding, you have an easier time, it seems, with some of those later levels. Whether or not that's true, hard to know for sure because it's our first time running this module, but I've definitely seen some people saying that. Okay, so yes, please work on this before this weekend. You want to get through some of these middle levels sooner rather than later, or you will be very sad this weekend. Okay, here is the status of things in this course. Honto, of course, dominating, but it seems like we've got some new people kind of climbing the ranks a bit, which is cool to see, and lots of very helpful people on here. Hey, we did an analysis of cryptography. We still have lots of thoughts about how cryptography went. And you can see right here that your frustrations with cryptography are backed by data, right? Like if you thought cryptography was terrible, you already know you're not alone, right? Everyone in the class knows they're not alone on that. But here's the hard data about how cryptography went, right? The median grade was a 55% on cryptography. We wanted to adjust that or to kind of aid with cryptography a bit. And what we did is we deployed a change for the late policy on the cryptography assignment where every single challenge you solve late, normally it's worth half credit, but for cryptography, we made it worth 75% credit. Highly encourage you to go back if you find some time to do that. But we also understand, right, this course moves at a fast pace. Most of you will not find time to go back and do it. So this, solution of, hey, 75% of you go back and do it, it probably doesn't really help the people that this assignment being difficult hurt the most. So we are addressing that. And we are addressing that with a 20% curve on the cryptography module. So everyone is just going to get 2% extra credit added to their overall grade. So if you solved everything, good job. You are like not getting punished for solving everything. Probably if you solved everything on crypto, you're going to do fine in this course regardless. But if you struggled, we're giving you a 20%, or no matter what, we're giving you a 20% curve on the cryptography module to bring it at least a little more in line with, for example, web security, which was a difficult assignment, computing 101, maybe the next most difficult after that. So we were adding a 20% curve to the cryptography module. So really simple math, there's 10 assignments. Each assignment is worth a total of 10%. We wanted to boost everyone's cryptography grade by 20% to account for the fact that we added new difficult challenges that people really struggled with. So 20% of 10%, we are giving everyone 2% overall extra credit in the class to kind of make up for the fact that, there were a few challenges for sure on cryptography that were harder than intended. Does anyone have any questions about that? Hopefully it just makes sense. Everyone's going to get 2% overall extra credit. It'll show up on your grade sometime this week. Any questions about that? Cool. Yeah. Hopefully we don't have to do that for any more assignments, but we'll see. Reverse engineering is a new module. I know some people are struggling. Start early, but worst case scenario, we understand. We're trying to work with you guys. If something is way too difficult, that is not our goal, but sometimes we miss the mark on what we're aiming for. And realistically, most of these assignments, you solve 60, 70% of the challenges, you're really getting the gist of the idea. That's great. And we want to encourage you to strive towards that 100%. But even generally speaking, 100% is not like what we're expecting. But we understand that cryptography was more difficult than anticipated. So that's what's going on there. Okay, I just realized I don't have the Twitch chat open. So if there's people on Twitch chat saying something about this, let me see if I can pull it up, just in case there is any confusion here. Well, it's not loading the past chat. If there's any confusion, message on Discord in the on topic for the course, and I will address that confusion after class. Okay, so that is the state of the course. Hopefully we all know, maybe understand that. And just to kind of put into perspective how far along we are in this course, right? We are on assignment, I believe, number 8. Yes, we're on assignment number 8, reverse engineering. There will be 2 more after that. And yeah, that's how it's going to go. Hopefully the next module will actually be a little bit easier than reverse engineering or crypto, possibly even easier than web security in some ways. Depends what kind of topics resonate with you. The last challenge, or the last module, though, after memory corruption, so memory corruption will be the next one. The last one is going to be a bit of a putting it all together module. It's kind of expected that might be a little bit tricky, and that is intentional in a lot of ways. But we're going to constantly monitor, the state of grades in the class. Anything we do that goes rogue and is crazy, we will make sure that grades are looking how we like to see the grades looking in the class. But yeah, that last assignment probably will be a little tricky because you'll be doing, something like cryptography over a web server and man-in-the-middling some network traffic. It's going to be combining all the concepts. So every concept you hate is coming back at the very last module. Maybe not a padding oracle attack, though. Maybe we'll not include that in the last module. Okay, cool. Any questions about the course or high-level questions about reverse engineering more specifically? Before I jump into a demo highly inspired by the current assignment. Not seeing any. Okay, cool. Let's see here then. Okay. So is this camera following me? It is. Okay. what I did here is I created a bonus challenge. Don't worry, you're not required to solve this bonus challenge. In fact, you probably won't even be able to find this bonus challenge. If someone wants to find the bonus challenge, let me know and I can make it more public. But what I did in a hope to demonstrate reverse engineering as I approach this topic, what I did is it was kind of tricky to teach reverse engineering. If you write the source code for the program, you're not really reverse engineering, right? You're like pretending to reverse engineer. So in an effort to kind of combat that at least a little bit, what I did is I wrote to ChatGPT and said, create this program modeled after this idea. And it spit out a bunch of source code. I didn't really look at it, compiled it, and that's this challenge. So I don't really know how this program works. I've got some high level understanding of how it works because I prompted ChatGPT with what it should do. But what we're going to do is, with that in mind, jump into understanding what it looks like. We're going to define some structs in IDA. Maybe we'll jump into GDB if we need to test some things. And that's kind of what we'll do. And if there's questions along the way, please just raise your hand or shout out what your question is, and we will roll with that. Okay, so I'm going to start up this demo challenge. And well, I guess we're going to want the desktop, aren't we? Because we are going to want IDA. So doing SSH isn't really going to help us very much. Here's what we got. We have this demo program. And the demo program, just to kind of double check, is a setuid elf. So it's just like the challenges you're working on, right? It's not like a Python script like many of the other modules might be. It is an elf. As in other words, if we obj dump this thing, which is going to make Jan very upset that I obj dumped this thing, but I'm doing it anyways, right? We just have a whole bunch of assembly. We have this main function. It was written in C and compiled, right? It wasn't just handwritten assembly. It was a C program that was compiled. It's got a main function, and maybe it's got some other functions. As a reminder, don't approach this assignment in obj dump. You're going to want a better tool or you're just kind of wasting your time. Okay, so I did obj dump just to show, hey, there's x86 instructions. You really, really, really want to use IDA or Ghidra or Binary Ninja or Anger Management or something to kind of dive into this a bit better. It will save you time, and believe me, you want to save time on this module. Okay, so what we're going to do then is, throwing away obj dump, we're going to type IDA64. You could also type, I think, Ghidra. Yeah, you could, well, I guess it's just going to launch Ghidra now because Ghidra is not very nice with argument. You could launch Ghidra. I'm going to launch IDA. And, I think in a previous lecture video last week, we showed off kind of loading a program into Ghidra. As I said, though, I am going to go to IDA. Okay, IDA64 challenge demo. A lot of people hit this issue. Hopefully everyone has gotten past this issue, but I think I still maybe got a message like 2 days ago about this. Hopefully you're done getting this, being panicked by this, right? This is just a warning. It says permission denied. Please specify another file path for the database. All this is saying is that it wants to create a file called challenge-demo.i64, and it can't do that because you don't have write permission in the challenge directory. It's a warning. Just hit OK. And then it's going to ask you where you want to save it. You can save it in your home directory. You could save it in temp. It doesn't really matter. Just save it somewhere you have the ability to write, which would be your home directory or temp. Okay, just do that. And then just hit OK. Don't worry about options. It's going to have smart options here. Okay, we get that. All right, now we're loaded in. And we can see a whole bunch of instructions. And we're in this nice graph view that we've seen in last week's lectures. I don't really even want to look at this right now. Maybe we'll decide that, I want to really understand the low-level control flow of the x86 instructions, and maybe, I'll appreciate that more later. I'm not really excited about that idea right now, though. What I want to do is I just want to hit tab, and this is what's going to fail in IDA on Sunday. So, start early or use Ghidra. Okay. I hit tab and it gives me information. I don't know, maybe IDA should just chill out on giving so much information, but probably there's people that appreciate this message. I don't know, I'm not one of them. Just hit okay. Whenever you're unsure, just hit okay. Okay, and now we've got some sort of C, right? It's not very good C. We've seen last week what this decompilation looks like, right? We've got variables like V3 and V4 and V5 and V7. There's not very good variable names. Almost certainly the original program did not have variable names that looked like this, but that's what we're working with. Okay, so what I am glancing at right here, trying to understand this program. And again, I told ChatGPT about this program. I haven't even read the source code for this program. I just told ChatGPT, create a program that does this sort of thing. So I don't know what this is going to look like totally. What I am looking for just on first glance is function calls and strings and like comparisons. These are like the control flow, like if or while or for, just like very subtly glancing at this, just high level, 10,000 feet picture of what's going on. Strings are nice because, as Jan talked about last week, is strings might provide some sort of like semantic anchor, I think is what he likes to call it. So for example, we can see this string right here says, failed to read number of rectangles. I mean, we'll see where that thing comes up. In fact, it's V5. Maybe I'll even want to rename this. So when V5 shows up later, I can see it better. We'll say like error rectangles message. And what I did to rename this is I just hit N. And you don't have to rename it, but maybe we're going to see this variable get referenced later, and it'd be helpful to have something better than V4 when it does, just so that at this high level view, I can see things better. We've got this V3 thing. I'm pointing at it because, my natural brain while lecturing is to go top down, but this is not how you actually reverse engineer. Who cares about top down? We're like as high up in the clouds as we can for looking at this thing. I'm literally just looking at strings. I'm seeing like, for example, in function calls, I'm seeing like some F reads in here. I'm seeing whatever this fprintf chk thing is. I see this render rectangle. I see this string right here. I see frame buffer matches. It's kind of nice that there's some symbols in this program that are, kind of strings give us semantic anchors. Function name symbols give us semantic anchors. I can see this right here. This looks very exciting. As soon as I see the string for /flag, I'm like, okay, so this is the goal. If somehow I can reach this fopen for flag, I guess we'll have to double check that it opens it, reads it, and then outputs it. But probably as soon as you see it's opening the flag, it might be promising. And let's see here. We'll call this flag file because I just want to quickly look at this. And then, I don't know, this is like some slightly optimized code that GCC emitted. For some reason, it's like V8 equals flag file. And you're like, why would we do this? And that's a good question. That basically the compiler did that / IDA's decompilation analysis is just trying its best here to like figure out what's going on. This decompilation effort is really just best effort. Like this, we can already see here like why V8, why do we need to do V8 equals flag file for us to close it? That doesn't really make sense. Like just cut this line out and then just close flag file. But here we are, it's decompilation, it's best effort. So we'll just say like flag file again. Maybe there's a more interesting reason that it does this, but probably it has to do with registers moving around, and it decided that in this case, yeah, we can actually see if we hover, it says RAX. I bet this one's like a different register, RBP. Why? Why did the compiler decide to both put it in RAX and RBP? Well, it put it in RAX, I guess, when fopen returned, right? If fopen returns, the value goes in RAX. It decided to put that then into RBP, probably to save it off because it's worried that it's going to call another function. And we know when we call a function, the return value goes into RAX. So it wanted to put it somewhere else. In fact, if we really want to, just quickly dive in here, right? We can see here, remember, just keep remembering this. This decompilation is best effort. It's not necessarily going to be very clean code. Call fopen, and then we see move RAX RBP. that's what happened. And then I guess it also tested off RAX. Maybe that's what really confused it. So it's checking if RAX is 0 or not, probably because it would be 0 if it failed. F open, we could read the man page, but it returns a null pointer if it fails. We would test RAX, and jump not 0 to basically have that error state. And I guess in analyzing this IDA's decompilation, gave us this mess of flag file and flag file again. That's just what's going on here. Looks like here my error rectangle message isn't very good because it gets reassigned later. So I guess it's not really just error rectangle message. It's, I guess, maybe just like error message because other people want to use it. So maybe I'll make that slightly more accurate. This nonsense here, again, just like the flag file again, we've got v4 equals standard error. And then we use v4 like just past standard error here. Best effort with this decompilation. So maybe we'll say like standard error again, right? Whatever we want to call it. Cool. And in this case, I'm getting more specific with analyzing this flag functionality. Realistically, again, if I wasn't lecturing, I would see open flag and I would just like ignore it. I would immediately jump up. I'd say, what is this condition? I want to get here. I want control flow to go to the open flag and, probably it's going to output. And we can see right here, F gets against F or V12. We're reading from the flag file. And then we're putting where we're reading. So, this is high level the logic that's going to now output that flag. Cool. So what we want to do is we want frame buffer matches to be true somehow. This needs to be not 0. So this is a function. This function, if I double click on it to get the decompilation of this, it does some stuff. I guess at the very end, it does a stir compare at the end. It says, return stir compare equals 0. If stir compare equals 0, that means that the strings match. Stir compare 0, they match. And so this is checking ultimately that 2 strings match. And what are those 2 strings? We're going to have to dig further in. But kind of building up this mental model, if I want the flag, I need 2 strings to match. Again, we don't know what those 2 strings are, but working backwards from our objective, we need 2 strings to match. That's what we've learned so far. Maybe we want to look in the middle a little bit more to kind of really kind of get an understanding of what kind of computations going on in the middle that might be related to those 2 strings we want to be equal to each other. Probably this stuff in the middle is somehow related to that. It could be totally unrelated. All this logic in the middle might have nothing to do with those 2 strings being equal. But, as we continue our high-level glance, let's just kind of see what's going on here. So we have our error message. Did I not change this to error message? What happened here? Thought I did rename. Error message. Cool. I like descriptive, correct things here. So error message. So if v3 does not equal 1, again, we're looking for strings, we're looking for functions, we're looking for conditions and control flow. If v3 does not equal 1, well, what that would mean here is that the output of f read, and we're reading into this pointer, so we'll call this pointer like my first read, I guess, because this is the very first read I see in this. So this is kind of the first place my input's going into this program. It's reading 4 bytes, 1 byte at a time from standard in. I think that's true. That, I didn't actually expect to see 4 arguments to f read. Let's go ahead and do man f read. F read takes a location. I've never seen this syntax before. This is mildly terrifying, but we'll say it's a buffer. Takes a buffer, takes a size, takes a number of members. That's kind of what I was guessing. And then where to read from. So what are we doing here? We're reading from standard input. We're reading into this location, 4 bytes, just 4 bytes. Basically, it's reading this argument times this argument many bytes. Cool. So we're reading in 4 bytes. My first read. We'll even say of 4 bytes. Who cares? It doesn't have to be the same type of variable name that you'd write in a real C program if you're writing it yourself. Just make it descriptive for yourself so that if I see this thing referenced later, which I see right here, I know that this is my first read of 4 bytes. Just make it a nice long variable name. Okay. And then this is first read result. Okay, so then we can see that our result is later referenced here, and it's checked to be if it is not equal to 1. If it is equal to 1, then we're going to go to label 11, whatever the heck that is. You know, remember C technically has go-tos. You probably don't use go-tos when you write C, but it is an option. You can go to something. It's just like an assembly jump, just aggressive control flow, go over here, which is going to print an error message, and then it'll fall through because you just fall through labels, and then it'll exit. So we definitely don't want to hit that. In fact, I don't even know. It doesn't equal 1. I would have guessed that fread would return the number of bytes read. What does it return? Let's see here. Return value, number of items read. Okay, so I guess that makes sense. Since technically we have an item size and then a number of items, and we said here that we're doing 1 item where each item is 4 bytes. So basically this means I read my 4 bytes, right? So you better give it 4 bytes, otherwise you're going to the error case. Cool. And it looks like that error case is going to have this error message of failed to read number of rectangles. So if you don't give it 4 bytes, you're going to fail. Okay, cool. High level understanding just like locked away in the background. If I'm unsure of this, maybe I don't trust my reversing ability to read this, we could test it. In fact, it might be a good idea in general to test as much as possible. So what I'm going to do is I'm going to SSH in. I'm going to clear this, and I am going to do, we're going to test for 4 bytes. So let's start with, so the way I'm going to test this quickly, you could use Python, you could use, create a file and redirect that file, whatever you like the most, okay? I kind of like echo -ne. -n means don't print a new line, and the E part means interpret stuff like this. Like this would be a capital A, and this would be a space, right? The hexadecimal thing that you're used to maybe in Python. What I'm going to do is, so if we do this, right, it's just nothingness. If I do x41, right, 41, which is an A, hopefully we understand how this works. Okay, so I am going to send it just 3 characters, right? If I send it 3 characters, I think we should get failed to read number of rectangles and the program should exit. Let's see if that is true. Failed to read number of rectangles. What if I give it 1 more byte? Right, we'll change this to an A so it's really easy to see. Well, we get a different error message. It's not happy with us, but our understanding is correct. You give it 4 bytes, it's happy. You give it less than 4 bytes, well, it's not happy. And you know, we could give it 5 bytes, probably, yeah, we get the same error message here. So we're at least making it past this failed condition, right? So right here, we know that our program at least got to right here. We don't know what this thing does yet, but it got here, which is kind of cool. We also don't know what the heck these 4 bytes are supposed to be. Now, that's not exactly true. Think back semantic anchor, and it says failed to read number of rectangles. There's a good chance that these 4 bytes, at least some of them, correspond to a number of rectangles. And if we want to immediately answer that question of, well, what is this? We can see that at least IDA's decompilation, which has its pros, has its faults, it thinks that my first read of 4 bytes is an int, and an int is a 4-byte value. We're passing 4 bytes, it's a 4-byte value, we're just reading straight into that int. I got a pretty good feeling that what we have here is a little endian integer. So for example, if I wanted to say that it is 1 rectangle, 1 number of rectangles, I might do this, right? I've got a pretty good feeling. We'll confirm that later. But this is being read in here, which is an int. Ints are always stored as little endian integers. in little endian architectures, which x86 is. And so these 4 bytes now is just, with XXD, little endian 1 as size 4 bytes. If we do challenge demo, well, we don't know necessarily that what I said is true because this error message doesn't somehow confirm that. It didn't say like failed to read rectangle 0 of how many rectangles maybe it's going to try to read, but we'll assume that right now we just pass a number of rectangles as 4-byte little endian integer. Okay, for loop. For loop always makes me a little nervous. That means there's going to be like stuff going on in a loop. It's going to be, multiple things happening. Probably it's not so scary, right? You've written a for loop before. For loops aren't the scariest thing in the world, but it's more complicated control flow than we've gotten to so far. So it is going from I equals 0. It is, this, right? This is how many times it's going to happen, right? You've written a for loop before. This looks like a pretty standard for loop where the goal is to do it my first read of 4 bytes number of times, right? So whatever the heck's going on the body of this for loop, right? All of this, well, the number of times that this is going to happen is whatever we passed in to our first read. So this, we're just going to call this number of rectangles, right? Let's make it even more specific. Before we only knew it was my first read of 4 bytes. Now we're going to get a little more specific. It's my number of rectangles. And we're about to do the inside of this that many times. Okay. Don't know what the heck this is. This looks terrible. What do you mean file pointer using ampersand of byte 5 and that's now v4? I'm just going to ignore this for right now. That looks terrible, but maybe not so consequential right now. Right? In fact, it's not even being used on the inside of this for loop, so that's a later problem. We'll even rename this to later problem. Okay. Then we're going to read into this location. So right now, IDA has decided to call the location we're going to read V11. And IDA's decompilation efforts, its automatic fancy analysis, has decided that this is 5 characters. Right? We can kind of see it. When I hover over, it says V11 character or bracket 5 bracket. It thinks this thing is a 5-byte buffer, which makes sense because it is doing a size of 5 and one of those things and from standard in. This is my next read. And we're going to do this in a loop. I guess we can fail out. In fact, we see right here, failed to read rectangle blah, which we saw here, failed to read rectangle blah. So this is where we're failing, right? Go to label 6. Again, this is like, here's what we'll do. We'll say this is label error. Wait, what? We'll call this error, and we'll call this exit. I don't know why these are 2 separate labels, but they are, I guess. However, you got a lot of things at play. We have like the decompilation analysis that's best effort. We got GCC that's emitting code in some kind of chaotic manner. I guess somehow, whether it's GCC or IDA's analysis, it decided that in one case, we put an error message here and then we F puts it, and then in this case, we do this. I don't know, but that is fine. We error here if we did not read our 5 bytes. So our next thing is we got to read 5 bytes. Let's even call this my 5-byte buffer I read. Again, variable names don't have to be like you would actually write in a program. Just make them descriptive. My 5-byte buffer I read. Okay, so we need to read in 5 bytes. Let's test this kind of theory, right? So I need 5 bytes. If I don't read in 5 bytes, I get failed to read rectangle. Let's get past this error message here of failed to read rectangle 0. Let's assume so far that we're correct here, that this means we're going to read 1 rectangle. We can test that also. And then let's give it 5 bytes. We'll just say A, B, C, D, E. I don't know what those 5 bytes are going to be. Well, we didn't get an error message. Something happened. So that's kind of cool. We'll have to figure out what the heck these 5 bytes actually are. But at least according to the program, we're not erroring. And let's actually test. Maybe we can do 2 rectangles, right? Let's go from 1 to 2. Now it says instead of failed to read rectangle 0, we failed to read rectangle 1. So then let's do another A, B, C, D, E. B, C, D, E, because we saw this thing's in a loop. And now we're still happy. Okay, so we figured out like how many bytes to give it in a kind of formulaic way in order to at least not get a failed message. And we also figured out what to do with these 4 bytes, that these 4 bytes determine how many bytes are going to be later read. These 4 bytes are a 4-byte little endian integer, and it is going to then read 5 times that integer number of bytes later, right? So we got this, and then we got 5 bytes, and then we've got another 5 bytes. That is what we have learned so far. We're just slowly collecting facts. If you think back to our zoom way back out again, doesn't feel like we've necessarily made progress on that stir compare thing, right? We had to compare 2 strings and they had to match. We haven't necessarily made very good progress on that, but that's okay because you're kind of guessing in your head where your effort is well spent, and probably understanding the structure of my input is probably going to be relevant knowledge for me to collect towards meeting this condition. Hopefully, maybe I'm wrong. Maybe this is all a side tangent and actually it has nothing to do with the flag, but probably it has something to do with the flag. Okay. Failed to read number of rectangles, failed to read rectangle number. And then one more thing happens in this loop, which is it calls a function. And it calls a function called render rectangle. And it passes in my 5-byte buffer I read. Well, this to me means this is a rectangle now, right? If we're going to render a rectangle and we're passing one argument to it, I got a good feeling that this thing right here we're passing to it is my rectangle. Could be totally wrong, in which case we'll rename our variable, but let's just, assume that we're not wrong. Okay. What does this function do? It does a whole bunch of stuff. We've got a for loop. We've got some if in there. We got some while in there. This might be some optimized code that GCC emitted that IDA is kind of struggling to recover the structure of in a very nice way. But we'll roll with it for now. And we're going to rename this thing right here, our parameter, right? By default, it decided that the parameter's name is A1. No, this is my rectangle. Okay, so now we can quickly see everywhere that rectangle is used. We can see that we're using offset 3. So remember, arrays are 0 base, so it's the 4th byte. We've got byte number 5 used right here. Got byte number 2 used right here, byte number 3 used right here, and probably byte number 0 used right here. Yeah, it's using it as a 1-byte value and dereferencing it, so byte number 0 right here. And something is going on with this. And one more thing that kind of jumped out to me is whatever the heck this frame buffer thing is. If I double click on this, looks like this is off in global memory. And it is going to be, I don't know, this thing called frame buffer. It's going to be a whole bunch of bytes. One thing I'll point out that I think is in the lecture videos, but I'll point it out anyways. This is in the BSS segment of memory. That sounds fancy. It probably doesn't matter for us. The only thing that I'm going to say about the fact that it's in the BSS, and you can see there's all these question marks in here. The BSS is different than the data segment of the program in that it is just all initialized to zeros. So the data section normally has a whole bunch of program specified bytes. The BSS is kind of just an optimization of the data segment where instead of just having a bunch of null bytes in your ELF, it just says, and then give me a BSS that's this size. It's just an efficiency thing because I can specify how many null bytes I want rather than a bunch of null bytes. That's what the BSS is. It's just a bunch of null bytes. Okay. And that is where this frame buffer thing is. Whoops. Okay. So somehow our rectangle, somehow these 5 bytes are being used with render rectangle. I'm not even going to look into it right now. We're going to ignore render rectangle. It's for our purposes right now, it renders the rectangle. Whatever the heck that means, if it becomes relevant to us, we will look into it. In fact, it probably will become relevant, but you know what? Allocating our time and energy towards just summarizing this as it's the rectangle renderer. Okay, and then we print frame buffer. So I noticed here that when I do, oh, I got disconnected. I noticed here that it's not just that it exits, it also gives me a whole bunch of empty space. So someone's outputting. If we wanted to see who the heck's outputting, we could, or, is this all happening once? No, it looks like, in fact, we have our read and then a bunch of 21 byte writes. So it's not even just a single write, it's a bunch of writes. Cool. Something about this feels very intentional, right? Like it almost feels like we have like an empty board or an empty canvas or an empty frame buffer, an empty something, and is being represented as a bunch of spaces, new line, bunch of spaces, new line. That's just a guess looking at this, but we will dive in. Hey, what does print frame buffer do? Well, it does in fact use that frame buffer that our render rectangle was somehow touching or using, or I don't know. We saw a render rectangle. I can type G to jump to something. Render rectangle. We can see that it uses frame buffer, right? Probably these two things are related. It makes sense their function names are related. If we have render, rectangle, print, frame buffer feel very related things. This does an fwrite. It is, actually, let's jump back. What are my arguments here? I'm getting 3 arguments to print frame buffer. Let's go back to main, G for go. Go to main. I don't know. This, I guess it's using my later problem, so maybe I need to understand this. It's using my error message. This error message variable that we've been using looks like it's kind of all over the place. We can see, for example, that this error message variable that IDA decided is a variable is just our RDI register, which is also our first argument. So maybe we'll say or first arg, because it looks like this decompilation isn't very good. Our error message, for example, right here, and then we go to error, and then it f puts error message or first arg. Guess what? This is the first arg. So it looks like this variable is kind of a little bit overloaded. It's just RDI. So RDI is getting passed here, and that is that, I guess. And then later problem is also getting passed here, which IDA seems to think is a file pointer, which is kind of interesting. And then one more interesting thing, this is where like decompilation, it feels like this decompilation is just failing us. We're gonna have to really think a little clearer here on this. It's passing 2 arguments, but then this thing thinks there's 3 arguments. So we're not even passing the 3rd argument. Something's off about this decompilation. These are just kind of the things you have to deal with. The alternative is just reading the x86 assembly, which you can do, but probably are like kind of weird decompilation. In a lot of cases is easier to read, even when it feels very broken like this, than just a bunch of x86. But if we need the ground truth, x86 is the ground truth. Okay, so we are taking a pointer to our frame buffer, which is off in the BSS, our global memory. We're just going to say frame buffer again, because if no one ever changes this thing, well, it does look like someone changes it. So maybe we'll say it's in a do while frame buffer plus 100. It looks like it's going over 100 bytes of this thing, just kind of do while, like glancing at this thing. We've got frame buffer again. Maybe we'll say frame buffer current or frame buffer I, or whatever feels good to you, because this thing is changing. It's changing by 20 every time through this loop. And we're seeing if it goes to frame buffer plus 100. If we just kind of glance and squint at this thing, it's going through a loop like 5 times, right? It's adding 20, and then it's adding 20, and then it's adding 20. It's checking until it's gone to plus 100. I might be off by 1 there. Maybe it's doing 4, maybe it's doing 6, but I think it's doing it 5 times, right? Because yeah, I guess we can be very specific here. Do while the first iteration always happens, then we add 20. Eventually the while gets checked at the very end because it's a do while. When we hit 100, yeah, so it's doing it 5 times. And we can see in here there's an F right and a put car. If we think back, put car 10, 10 is new line. We can make this crystal clear to ourselves by changing it to a character instead of a decimal. It's a new line. It is printing hex 14. This is like a mess, right? Like, why are you showing me decimal here, octal here, decimal here? Just make this decimal also, because I have a pretty good feeling, yeah, these two things line up. So it's giving us V4, which this is not great. We'll say frame buffer. Actually, we're going to call this, reading this structure, here's what feels right to me. We're going to call this like frame buffer next. And then we're going to call this one frame buffer current. And the reason I'm going to call it that is because it saves this off here, and then it adds 20 here. Like, you'd imagine this happening at the end and then just using one variable. Best effort. Does anyone have any confusion about like what I'm saying here, right? Like, it's using a lot of variables when probably the original source didn't quite use so many variables, but technically this logic works. Like, we can save off frame buffer next and then increment at the beginning of the loop instead of the end of the loop, as long as we keep track of the original. It's not very good, but does anyone not understand what I'm saying here with like this multi-variable mess? Okay. Yeah, sometimes it's literally just a matter of like staring at these 6 lines for like 5 minutes until it makes sense. Like, the decompilation here is not lying to us. It's just not clean. Okay, so frame buffer current is frame buffer next. Then we increment to go to 20. And then what we're doing is we're outputting frame buffer current. We're doing one of those things. Each of them is size 20, standard out, new line. So 21 characters total, including the new line, is written out 5 times. Look at this. 5 times 21 characters, right? So this right here corresponds to these write system calls. F write, put car. If you're wondering why it's like, maybe you have a natural question, might be, why is it doing a write of 21 instead of a write of 20 followed by a write of 1? Which would be a pretty good question. The reason it's doing that is because we're not actually calling write. We're calling libc functions. We're calling fwrite and putcar. And libc has an internal buffer. It's buffering things. So what libc is actually doing when we're calling into all of these functions, by default, it's set up to line buffering mode. And what libc is doing is it's just like filling in this buffer and waiting for a new line character. And as soon as there's a new line character, then it does a write system call to output everything up to and including the new line character. And then it starts filling up the buffer even more. So that's why these two things are getting collapsed into a single syscall. It's because libc has fancy buffering stuff going on here. Okay. So here's what I'm going to do, just because this control flow is terrible. I'll show you another thing in IDA. I think if I hit slash, it says, please enter comment. 5, we'll say output 20 characters and a new line. Do that 5 times, right? This is how I would summarize all of this logic. In fact, maybe we don't even want that right here. Maybe we'll, did I lose my comment? I don't want to lose my comment. Can I not copy? That's very sad. What if I right click copy? Okay, cut. Okay, put the comment at the very top of the function, because that's what this function does. Right? Maybe we want to leave little notes for ourselves because we're going to forget what the heck print frame buffer does. But outputs 20 characters and a new line. Do that 5 times. And it's indexing based off of frame buffer. So it seems like this frame buffer guy, let's see here. It seems like this guy's 100 bytes, right? Because it's doing like 20 bytes and then the next 20 bytes and then the next 20. And it looks like it's like 20 bytes. And then another, so it's like 20 and then 20 and then 20 and then 20 and then 20. It seems like this is like a YX grid, right? You could kind of think of it as that. Seems like it is like basically, what do I want to say? Basically, it feels like it's frame buffer. What is the right C syntax for this? Car frame buffer of 5 of 20. I think that's the right syntax, right? I'm pretty sure, right? It feels like this is like what this type is. It's 5 things of 20. Or you could say it's 1 thing of 100 if you prefer that, but let's be even more explicit. It's 5 things of 20. So let's see, maybe we can even change this. Frame buffer y, we'll say car frame buffer, and I said it is 5 of 20. Okay. Well, it decided that it's going to make it 100 for us. Guess it doesn't like this whole nested thing, but fine. It's 100. In our heads, though, we're going to remember it is 20 and 5 also. Cool. So let's go back then to main. So we print the frame buffer. It seems like these arguments are entirely irrelevant, like, and including this later problem. We'll even call this like not a problem because we don't care about this thing. This is just an artifact of the x86 or something. Okay, this right here looks super interesting. This is a big string that has hello world in it and a bunch of star characters and some more star characters. This seems pretty interesting. We're going to call this hello world buffer because these bytes are getting copied into hello world buffer. And our frame buffer matches is actually comparing hello world buffer with whatever the heck this is. Wait, what? What is this guy? Is this a global? This is read-only data. Oh, this is here. Wait, what the? Hold on. It looks like this thing is the same as this thing, right? In fact, if I hit tab, we could see, yeah, it's actually using a hello world, this thing off in the data section. And the data section, again, is not 0 initialized. It's initialized to whatever the bytes are. Okay, so this thing is 106 bytes. Kind of interesting that it's close to 100 bytes. In fact, actually, if we think about the fact that we're outputting 21 5 times, that would be 105 bytes. So maybe, you know, a null byte at the end or something like that. So it seems very related. Start copy hello world buffer. So it's taking this data, putting it in here, and then also doing this. Okay, what is this frame buffer matches? It's taking a lot of arguments. I'm a little bit skeptical here. So the stir compare ultimately goes off of V5. This goes off of S1. Oh, I guess all of this is getting passed through to frame buffer 2 string. Okay. Okay, so hold on. Let's zoom out here. So we have, there's kind of a few things in my head right now of what's going on, worth investigating to understand this program. So ultimately, we're really interested in this frame buffer matches thing, which is receiving 2, 3, 4, 5 arguments, allegedly. Let's see here also. I don't know what these arguments are, but we've got this whole frame buffer matches direction, which inside of frame buffer matches calls frame buffer to string and then ultimately does a stir compare. And then frame buffer to string uses the frame buffer and then does a whole bunch of stuff. And then we also have the whole render rectangle thing that maybe we need to understand as well. Okay, so we could go in either direction. We could either now work on understanding render rectangle or work on understanding the other thing. the frame buffer matches guy. I'm going to work on frame buffer matches. I got a feeling we're going to have to understand render rectangle, but this guy is more directly related to the flag, so I'm going to work on understanding it first, and then we'll go back to render rectangle. Okay, this guy, frame buffer to string, I'm just high level looking at this, stir compare S1. This is part of my comparison, or we'll say compare 1, and then we'll call v5 compare 2. These are the two guys I really care about. So compare 1 gets passed in here. Value may be undefined for compare 2. That's unfortunate. We're going to have to figure out what the heck's going on here for our stir compare, because stir compare is definitely using something. Compare 1, though, frame buffer to string. Okay, so compare 1 is getting set up to be 106 bytes on our stack. It's a local variable inside of frame buffer matches. And then that location in memory on our stack is getting passed to frame buffer to string. So I got a pretty good feeling that this function is outputting, it's putting bytes into memory here, right? This is 106 bytes, it's passing that pointer off to this function. I got a good feeling that the return, the result of frame buffer to string is going in here. So we'll say like, and string result or something. So this seems to be probably where it's going in. This is saying 106, probably that's like the size, right? It's passing the size. And then A3, A4, A5, A1, I don't know, maybe these things will do something. Could again be IDA messing with us a little bit and passing more arguments where there are none. Okay, frame buffer to string. This, I think, is going to be my input buffer / output buffer. It's like, this is my buffer, I guess we'll just say. And then let's quickly look at this. V2 is frame buffer. We're going to do the thing where we say frame buffer again, because it is based off of frame buffer. It looks like it's going up 20 every time, right? We've got this loop. While result is not equal buffer plus 105, result equals buffer. Okay, so we're taking our input buffer, we're serving it off into this results variable, which is a pointer. Every time through this loop, it's going up 21, which is our 20 plus our 1 new line character, probably related. Frame buffer again goes up 20 every time. So one of them is going up 21 every time. One of them is going up 20 every time. One of them seems to be like our frame buffer of our raw characters. And one of them seems to be the thing that gets printed out to the screen. Result minus 21 equals V4. Okay, so this right here is messing with results. So ultimately, everything is going out through the results. This right here is writing to memory. Okay, it's writing V4. What the heck is an O word? I've never seen an O word in my life. O word. I mean, I would guess quad word being 4, and then O word maybe being octa word. Maybe this is 128 bytes. Let's look at, okay, yep, it's this XMM nonsense. You might notice this in the disassembly. This is 128 bits of data, these XMM registers. You know, someone decided 64 wasn't enough. They moved to 128. That's in this XMM stuff. It has to do with vectorized instructions. Honestly, we don't really care too much other than the fact that it's an O word, which is 128 bytes or 128 bits. It is 16 bytes of data. So we are taking, we'll just say this thing is 16 bytes of data. In fact, what? You don't like that? Data 16 bytes. In fact, we can see right here that IDA says it's an int 128. So yeah. So we're taking 16 bytes out of frame buffer / frame buffer again. Okay. And then we're looking at results minus 21. So this whole business where we increment at the beginning and then subtract after the fact. Basically, we're looking at result and then just pretend that result plus equals 21 happens at the end. We're taking result. We're looking at 16 bytes of it, right? So we take results. Again, just pretend that minus 21 isn't there because there's a plus 21 up here. Turn this into a 128-bit pointer, and then define it. So we just took 16 bytes of data from frame buffer and wrote it out to result. So this just copied 16 bytes of data from the frame buffer into my output buffer / input buffer. And then looks like we go 16 bytes into that because it's result -5 instead of result 21, which is 16 bytes further. And then we cast this to a D-word pointer, which is 4 bytes. So a D-word pointer, look at 4 bytes, subtract 1, blah, 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 blah. This is, I think, copying the last 4 bytes. So I think between this and this is how it's doing 20 bytes of movement. And then what is it doing at the very end? It's kind of probably as you might be expecting based on what we've been seeing. It is then assigning the very last byte to be a new line character. So it's like taking 20 bytes out, adding a new line character. And ultimately what we're doing is we're transforming this thing where it's 5 rows of 20 bytes, and it's turning it into 5 rows of 21 bytes, where the very last byte is a new line character. That's all it's done here. It's just added a new line character to the end of each of these rows, 20 to 21. Add a new line, 5 of those things. And then, as we guessed, remember, if you think a little bit back, we're talking about how there was 1 extra byte, and we're thinking maybe, based off of our size calculation guesses, it might be a null byte. We don't have to look at the exact math here. Probably this is lining up with what we said. It's a null byte. A null byte. So ultimately, and we get more specific, we could dig deeper into this to see if we're wrong about things. It seems like it's just turning our 100 bytes into 106 bytes. Okay, so we had a 100-byte thing, and now we have a 106-byte thing because 5 new line characters and a null byte was added to the end. Let's go back to main. Frame, but where were we? This thing, frame buffer matches. So we did frame buffer to string. This thing right here now contains my 106 bytes, which is based off of the frame buffer, but with new lines and a null byte at the end. This looks like, I don't know, we don't care about this. This is what happened, okay? We're just gonna assume that's true. And then we're getting a comparison against this undefined thing. We gotta figure out what the heck this guy is. If I look at the actual x86, this stir compare needs to be taking in RSI is my second argument, right? RDI first argument, RSI second argument. That comes from R9. R9 comes from RDI, and that is the beginning of the function, which means that our very first parameter into this, so this is where you kind of got to sometimes look at the x86. This is actually the first point where the decompilation is just wrong. Everywhere else, it's been like confusing-ish. In this case, it says compare to value may be undefined. It has no idea who the heck this is. But it's this guy. It's A1. Because as I just said, look at this again. RSI is R9. So IDA thinks that compare to is R9. If we look at the hover, the very right, it says it's R9. We look into this. R9 becomes RSI, which is the second argument passed to stir compare. And R9 comes from RDI. RDI comes from being the first argument passed to whatever this function is, because that's the calling convention. Okay, so this thing right here is frame, we'll just say it's my first arg passed. Okay, even though it's like confused and nothing makes sense, we'll say compare to. Okay, so whenever it gets passed here, the second thing passed to this is part of my comparison. So let's go back here. What is my second thing passed? Well, it is this thing right here. Okay, so I honestly, looking at this, I'm a little confused. I'm like, what the heck is this? What the heck is this? My next step is going to be to look at render rectangle and hope that it makes some sense of this. And I realize we're running out of time. So worst case scenario, if we run out of time, I'll do a bonus stream tomorrow where we get to the bottom of all of this. I think what we're going to want to do is figure out the frame buffer here. So actually, hold on. Let's take a step back. If we go to main, I'm realizing now maybe that I'm not so confused with this comparison. All we said that we care about for frame buffer matches so far is this first argument, okay? Hello world buffer, which came in being copied from here and it ended up here. I think that the rest of these arguments aren't actually getting passed in. I have a feeling that frame buffer matches really just takes one argument, because compared to my first arg passed, right, this is identical to this, right? I think all it's taking is one argument. And then we have that global memory buffer thing that was containing the frame buffer. I've got a feeling that it's just comparing against that, because it's taking our frame buffer, converting it into a string, and then that ends up here, that ends up on this side of the comparison, this ends up on this side of the comparison, which we said is our first argument. These things are identical. I think these extra arguments are just a lie. There's no extra arguments. So if I hit Y on this, to change the type definition of this function, I can actually just, whoa, what the heck happened there? Okay, I can just say there is no other arguments. I think I can do that. Maybe not so much. It's not liking that actually. Hold on, let's try. Bad declaration. Well, we can also just not dig into if there's a way to represent this in IDA. Edit func. Okay, we'll just add a comment instead. There is actually only one arg we care about, the first one. So we'll just leave that as a note for ourselves, and that this is this and this are all the same. It ultimately gets compared with our frame buffer converted to a string. And so my frame buffer converted to a string needs to be equal to whatever the first argument is that got passed in. So let's go back to main. That something is this, because it's hello world buffer, the first thing passed. It's this. And this right here looks like it could totally be 106 characters. In fact, if we copy this and we open another terminal, maybe that will help clear things up. Open terminal, Python, paste, oops, 105 plus a null byte. So somehow we need to put this into our frame buffer. Now, unfortunately, we're out of time. And also, unfortunately, we haven't figured out exactly the render rectangle functionality, right? If we think back to when we were actually interacting with things, we figured out how to like pass something, but we didn't figure out what this ABCDE actually represented. Probably it represents what's going to go on in render rectangle to fill this in. And once we figure that out, we can figure out how to make the state of the buffer be this hello world business. In fact, if we print this instead of take the length of it, we can see that this looks like it's the same size, right? We just have to figure out how to make this be hello world. We'll finish that out in the stream tomorrow. I'll run a stream tomorrow where we get to the bottom of this. And that is that. Okay, thank you all for attending, and good luck on the assignment. Please start early, or like start now. It's going to be difficult. The first few challenges after the deadline are difficult, or after the checkpoint are difficult. Then maybe it gets a little easier. Okay, goodbye.